नमस्कार, मेरा नाम सोम है।
और मैं मुकेश कुमार कृष्ण।
आज हम इक्वेशन ऑफ मोशन के केस नंबर 3 पे बातचीत करने वाले हैं।
तो चलिए शुरू करते हैं। आइए।
Hello everyone, today we are going to discuss case number 3 of equation of motion. In this, we are going to explain this complex engineering problem into simple terms. So let's start what the problem is. First, I should break down the problem. The setup includes two concentric cylinders. The outer one is rotating at a constant angular velocity. This causes the inner bob to twist due to viscous torque. What really happening is the outer cylinder is rotating at velocity of r omega, which causes the fluid to move, which causes the inner bob to move at a certain angular velocity. I need to recall the basics of viscosity in cylindrical coordinates. So specifically tangential flow between rotating cylinders. Since it's a Newtonian fluid, the stress is proportional to the velocity gradient. The key equation here would involve the torque balance, the viscous torque from the fluid equals to the torsional torque from the spring. The rotating viscous fluid comes causes the suspended bob to turn. The torque produced by the momentum transfer in the fluid equals the product of the torsion constant k and the angular displacement theta b of the blob. The angular displacement can be measured by observing the deflection of light beam reflected from a mirror mounted on the bob. So what here happening is that a mirror is placed on the blob, which whenever some kind of angular displacement is happening, the beam which is being reflected of the mirror gets deflected. So through that we can calculate the angular displacement. So now Mox will further explain.
Okay, I should start by explaining this setup in detail. Then move to the Navier-Stokes equation, simplified. For this case, since it's a steady, laminar, and tangential flow, the radial and axial components can be neglected. The theta component of the momentum equation in cylindrical coordinates would be relevant. Assuming no end effects, the flow is purely tangential and varies only with radius. The velocity profile v underscore theta needs to be determined. Then compute the shear stress on the inner cylinder bob. Okay, which depends on the velocity gradient. Shear stress is u into dv under dv theta divided by dr minus v theta divided by r for a Newtonian fluid. Once the shear stress is found, the torque on the bob is the stress multiplied by the surface area and radius. Setting the set is equal to kt into theta b gives an equation to solve for u.
So the assumptions which we are going to take in this question to make it solvable are the conditions of measurements are controlled so that there is a steady tangential laminar flow in the angular region between the two coaxial cylinders shown in the figure. So what we are going to take is the flow should be happening between the tangential should be steady, tangential and laminar. So because of the arrangement used, all L effects, including the bob length, are negligible. And we are going to express and calculate viscosity of fluid, assuming that the fluid in space behave like Newtonian fluid. But wait, I want to check the boundary conditions also. The outer cylinder rotates at omega naught. So at r outer is equal to v theta is equal to r omega. Outer the inner bob is at rest, but due to the torque, it twists by theta b. However, since the bob is suspended, its rotation is resisted by the torsion constant. So the torque from the fluid must equal to the torsional torque. Wait, maybe the inner cylinder bob isn't rotating because the torsion wire resisted. So the angular displacement theta b is the result. The key is that the velocity at the inner surface R inner is 0 because the bob isn't moving, except for the small twist theta b which might be static. Or is the bob rotating at some angular velocity, omega? Bob due to torque? Maybe I need to clarify. In a typical viscosimeter, the inner cylinder is stationary and the outer rotates. The torque on the inner cylinder is measured. Here, the bob is suspended with a torsion wire. So, when the outer cylinder rotates, the fluid transmits torque to the bob, causing it to twist until the torsional torque equals to the viscous torque. So, at steady state, the bob isn't moving. It's stationary but twisted by angle theta b. So, the velocity at r is equal to r inner is 0. The outer cylinder V theta is equal to omega r outer at r is equal to r outer. So the velocity profile between r inner and r outer is such that the V theta satisfies the Navier-Stokes equation for this geometry. Now we will understand that which Navier-Stokes equation we are going to use and why we are going to use that Navier-Stokes equation. So let proceed to the next part of the problem. So now Moksh will explain what is Navier-Stokes equation, why we are using it in this question, and all about Navier-Stokes
Okay,
equation.
guys, we are diving into one of the most powerful tools in fluid dynamics, the Navier-Stokes equation. This equation are the rules of the game for how fluid behave, from blood flowing in our veins to the air rushing over an airplane wing. But why they are so critical in transport phenomena? Let's break it down. Transport phenomena are all about how stuff moves. Think of three key players: momentum, energy, mass. The Navier-Stokes equations are the superstar of momentum transport. They tell us how fluid accelerate, slow down, linking forces like pressure and viscosity to motion. Without them, we couldn't design pumps and predict weather, or even model blood flow. Okay, why we use Navier-Stokes in transport phenomena? Imagine you're designing a new drug delivery system. You need to know, will the drug mix properly? Will the pump handle the pressure? Navier-Stokes answer this by modeling convection diffusion forces. But it's not just about fluids in pipes. These equations coupled with heat and mass transfer. For example, in a car engine, hot gas expands heat transfer. Fuel mixed with air, mass transfer. All driven by fluid flow, momentum transfer. Okay. Real world application. Let's see where Navier-Stokes saves the day. Aerospace, simulating airflow over wings to reduce drag. Biomedical, modeling blood flow to prevent uh, aneurysms. जो भी है. Uh, Next, energy, optimizing wind turbine blades for maximum efficiency. And last one is environment, predicting oil spills or pollutant dispersal in rivers. Even your morning coffee stare, the Navy stocks in action, the dark side, challenge and limitations. But Navy stocks is not all sunshine and rainbows. Here's why. Turbulence, the non-linear term, creates chaotic, unsolvable patterns. We need supercomputers to simulate it. Analytical nightmares, exact solution exist only for simple cases like flow between two plates. Real world problems, hello, numerical methods. And third is assumption. They assume fluids are continuous, but in space or nanotech, fluids behave oddly. Okay. Next is since and the future beyond today's limits. Quantum computing, crack turbulence, mysteries, fastest. AI and machine learning train models to predict flow without the brute force calculation. And last is multiphysics, combined fluid dynamics with electromagnetism or biology. Okay, closing scene. Next time, अरे इसको बंद कर दे, pause कर दे, इतना काफी है.
Hello, now we are going to explain that which Navier-Stokes equation we are going to use among every. So we have around 9 Navier-Stokes equation, out of which we are going to use some of them. Now let's start Navier-Stokes equation. So we are going to use Navier-Stokes equation. First we have to see it in Cartesian coordinate. In Cartesian coordinate we have three equations. So let's see the first equation. This is an x equation of motion. Now let's see y motion, y equation of motion. Now z equation of motion. But the Navier-Stokes equation, we won't be using this all three of them, because the coordinate system over here it is indifferent. So this is the one example which I have given over here. Here we are going to use not Cartesian plane, but we are going to use it in cylindrical coordinate. This was just one of the example which I gave. The equation which we are going to use today in this question are in cylindrical coordinate system. So in cylindrical we have three types: R equation of motion, theta equation of motion, and Z equation of motion. So let's see for R equation of motion. So this is our r equation of motion and this is our theta equation of motion. Now we will write for z equation of motion. So for z equation of motion, our equation is P into dou Vz by dou t plus Vr into dou Vz by dou r plus V theta by r into dou Vz by dou theta plus Vz dou Vz by dou z is equal to minus dou P by dou z plus mu 1 by r dou by dou r into r dou Vz by dou r plus 1 by r square into dou square Vz by dou theta square plus dou square Vz by dou z square plus rho gz. In this question we are going to use cylindrical coordinate and we have three equation of motion in r equation, theta equation and z equation. In next video we will explain in detailed form that depending on the velocity how we reduce this equation into simpler terms. In this equation most of the terms are going to be zero and the equation is going to be short, so we will explain it in next video. For this video, thanks for watching this video.